CPU versus GPU, why thousands of GPU cores do not replace the CPU. Chapter 1. Gate and Kernel opening. Welcome to Gate and Kernel, where we explain how computers really work, from the logic gates inside a processor to the operating system kernel that controls the machine. Today, we are comparing the CPU and the GPU. A modern GPU may contain thousands of computing units, while a desktop CPU may contain only 8, 12, or 16 cores. So why does the GPU not replace the CPU? Let us begin. Chapter 2. Why thousands of GPU cores do not replace the CPU. At first glance, the comparison seems unfair. If a GPU has thousands of cores and a CPU has only a handful, the GPU may seem thousands of times more powerful. But a CPU core and a GPU core are designed for different work. A CPU handles complex instructions, unpredictable decisions, operating system tasks, and low-latency workloads. A GPU performs large numbers of similar calculations at the same time. The two processors solve different problems. Modern computers need both. Chapter 3. What is a CPU? The Central Processing Unit, or CPU, is the main general-purpose processor in a computer. It runs the operating system, launches applications, manages files, handles user input, controls devices, processes network activity, and coordinates the system. A modern CPU core can execute arithmetic, logic, branches, memory operations, system calls, and interrupt handling code. It must also switch quickly between unrelated tasks. For this reason, a CPU core includes sophisticated hardware such as branch prediction, out-of-order execution, several cache levels, memory protection, and virtual memory support. The CPU is optimized for low latency. Its goal is to finish important and unpredictable tasks quickly. Chapter 4. What is a GPU? The Graphics Processing Unit, or GPU, was originally designed to accelerate computer graphics. Rendering a three-dimensional scene requires enormous numbers of similar calculations involving vertices, pixels, textures, lighting, shadows, reflections, and filters. Many of these calculations are highly parallel. The color of one pixel can often be calculated independently from another. Instead of processing pixels one at a time, a GPU can process many pixels simultaneously. Modern GPUs also accelerate artificial intelligence, scientific simulations, video encoding, image processing, engineering, data analytics, and weather modeling. A GPU is optimized for throughput, completing an enormous amount of similar work over time. Chapter 5. CPU cores and GPU cores are not equivalent. The word core creates confusion. A CPU core is a powerful and largely independent processor. It can execute complex instructions, make decisions, handle interrupts, run operating system code, and work with irregular control flow. A GPU core is usually a much smaller arithmetic execution resource. These resources may be called CUDA cores, stream processors, shader processors, execution units, vector lanes, or arithmetic logic units. A GPU with several thousand cores does not contain several thousand complete CPU-like processors. Its arithmetic units are grouped into larger structures, and many threads share control hardware, caches, registers, and scheduling resources. This saves space and power, but makes individual GPU threads less independent. Chapter 6. A few powerful cores versus thousands of simpler units. A processor has a limited transistor budget. A CPU spends many transistors on making individual instruction streams run faster. It uses hardware for branch prediction, instruction reordering, cache management, dependency tracking, and precise control. A GPU spends much more chip area on arithmetic throughput. Imagine multiplying 1 million numbers by the same value. A CPU can process several numbers at once. A GPU can divide the work among thousands of threads. Now imagine a program that must read a file, open a network connection, wait for a response, choose between several paths, update a database, and handle errors. That task contains branches, dependencies, delays, and system calls. A CPU is much better suited to it. Chapter 7. Latency versus throughput. Latency is the time required to complete one task. Throughput is the amount of work completed during a period of time. A CPU is optimized to reduce the latency of individual tasks. A GPU is optimized to maximize throughput across many tasks. Think of a restaurant. A CPU is like a skilled chef who can prepare different meals and respond to special requests. A GPU is like a production line designed to prepare thousands of similar meals. The production line produces more meals per hour, but it is not necessarily better at preparing one customized meal. Likewise, a GPU may be inefficient when a task is small, sequential, unpredictable, or filled with different branches. Chapter 8. How GPUs execute thousands of threads. GPUs run very large numbers of lightweight threads. However, these threads are not always completely independent. Many GPUs execute groups of threads that perform the same instruction at the same time on different data. NVIDIA calls this SIMT, or single instruction, multiple threads. A group of threads is often called a warp. AMD uses a related concept called a wavefront. Imagine 32 threads processing 32 pixels. All threads may calculate brightness at the same time, using different pixels. The problem appears when threads take different branches. The GPU may need to execute both paths separately, leaving some execution lanes idle. This is called branch divergence. CPU cores are generally better at handling complicated and unpredictable branches. Chapter 9. Why the CPU still controls the computer. A computer requires much more than arithmetic throughput. The operating system depends on the CPU for process scheduling, virtual memory, interrupts, storage, networking, security, device drivers, file systems, user input, and application coordination. Consider opening a file. The system must interpret the path, check permissions, search file system metadata, locate the data, allocate memory, ask a driver to read the storage device, handle an interrupt, copy the data, and report errors. This is not a batch of identical calculations. It is a chain of different operations, and many steps depend on earlier results. The CPU is designed for exactly this type of work. That is why it remains the main control processor. Chapter 10. The GPU usually depends on the CPU in many systems. The GPU operates as an accelerator. The CPU launches the application, prepares data, allocates resources, transfers or maps memory, and submits commands. The GPU executes thousands of parallel threads and stores the results. The CPU then displays, saves, or transfers those results. In a game, the CPU may handle game logic, character behavior, physics coordination, input, audio, networking, scene preparation, and draw calls. The GPU may handle geometry, rasterization, texture sampling, pixel shading, lighting, ray tracing, and image reconstruction. A powerful GPU paired with a slow CPU can create a bottleneck because the GPU must wait for more work. Chapter 11. Why every program cannot use thousands of GPU cores. A problem must contain enough parallel work to use a GPU effectively. Some tasks are parallel. Others are sequential. Suppose step B needs the result of step A, step C needs step B, and step D needs step C. These steps cannot run at the same time. Real programs often contain both parallel and sequential sections. Only the parallel section can be accelerated. This is related to Amdahl's law. If only half of a program can be accelerated, making that half infinitely fast still cannot make the whole program more than twice as fast. There is also overhead from memory allocation, data transfer, kernel loading, command submission, synchronization, and result transfer. For a small task, that overhead may cost more than using the CPU's. Chapter 12. Memory architecture matters. A CPU normally has several levels of low latency cache. A common hierarchy includes L1 cache, L2 cache, shared L3 cache, and main system memory. The CPU uses cache logic and prefetching to reduce waiting time. A GPU often has much greater memory bandwidth. High-end GPUs use specialized memory systems designed to move enormous amounts of data. However, high bandwidth is not the same as low latency. A GPU often hides memory delays by switching between groups of threads. When one group waits for data, another group uses the execution units. The CPU tries to reduce delay for a smaller number of active threads. The GPU tries to keep many threads busy. Chapter 13. Dedicated GPUs and data transfer overhead. A dedicated GPU normally has its own video memory, or VRAM. The CPU uses system memory, while the GPU uses graphics memory. Data may need to move between them through PCI Express. This transfer can become a bottleneck. Suppose a GPU calculation takes 1 millisecond, but moving the input and output takes 5 milliseconds. The total operation takes at least 6 milliseconds. Arithmetic speed is not the only factor. Programmers must also consider transfer size, transfer frequency, memory layout, synchronization, kernel launch overhead, cache behavior, and data reuse. Efficient programs keep data close to the GPU and perform enough work to justify the transfer cost. Chapter 14. Integrated GPUs change the memory model. An integrated GPU is located inside the same processor package, or on the same chip, as the CPU. Integrated GPUs commonly share system memory with CPU cores. This can reduce the need to copy data between separate memory systems. Modern system-on-a-chip designs may allow CPU cores, GPU units, and other accelerators to access shared memory. However, shared memory does not make the CPU and GPU identical. They still contain different execution hardware and remain optimized for different workloads. The main advantage is faster communication and improved energy efficiency. This is useful in laptops, smartphones, tablets, small computers, game consoles, and efficient workstations. Chapter 15. Why GPUs are so effective for artificial intelligence. Modern artificial intelligence workloads rely heavily on matrix and vector operations. A neural network may perform enormous numbers of multiply and accumulate calculations. Many matrix elements can be calculated independently. A GPU can distribute this work across thousands of execution units. Modern GPUs may also include tensor cores and other specialized AI hardware. But the CPU remains necessary. It loads the model, prepares input data, manages files, runs application logic, schedules GPU work, handles network requests, processes user commands, coordinates accelerators, and manages errors. During inference, the GPU performs much of the matrix math, while the CPU runs the surrounding application. During training, the CPU also manages data loading, pre-processing, storage, and networking. Chapter 16. Why operating systems do not simply run on GPUs. A general-purpose operating system requires interrupts, exceptions, privilege levels, virtual memory, process isolation, precise control flow, device management, context switching, low-latency response, and complex system calls. Traditional GPUs were not designed for these responsibilities. GPU threads are optimized for parallel numerical work. They are not normally intended to run complete desktop applications independently, respond to every hardware interrupt, or manage a conventional operating system. Modern GPUs are becoming more programmable. Some include advanced scheduling, memory management, and virtualization. However, the basic division of labor remains. The CPU is the general-purpose control processor. The GPU is the high-throughput accelerator. Chapter 17. Workloads that favor the CPU and the GPU. A CPU is usually better for complex branching, sequential dependencies, small datasets, low-latency work, irregular memory access, frequent system calls, complicated logic, and heavy operating system interaction. Examples include operating system services, browser logic, compilers, database transactions, file compression, application startup, scripting languages, device drivers, and many server workloads. A GPU is usually better for large amounts of parallel data, repeated arithmetic, similar instructions, high memory bandwidth, and enough work to hide overhead. Examples include three-dimensional graphics, neural network training, neural network inference, image filtering, video processing, scientific simulations, matrix multiplication, rendering, and large-scale data processing. The best CPU workloads need flexible control and fast response. The best GPU workloads contain thousands or millions of similar tasks. Chapter 18. CPU and GPU comparison. The CPU focuses on low latency. The GPU focuses on high throughput. A CPU contains a few powerful cores. A GPU contains many simpler execution units. A CPU handles complex branching well. A GPU works best when many threads follow similar instruction paths. CPU parallelism is limited to moderate. GPU parallelism can be massive. The CPU uses sophisticated caches to reduce delay. The GPU memory system supports many active threads and high bandwidth. The CPU runs the main operating system and complete applications. The GPU usually works as an accelerator and depends on CPU coordination. Chapter 19. Can a GPU replace a CPU in the future? GPUs will continue to become more capable. They may gain better scheduling, more flexible control flow, improved memory systems, stronger virtualization, and more independent execution. At the same time, CPUs are becoming more parallel. Modern CPUs may include more cores, wider vector instructions, AI accelerators, integrated GPUs, media engines, and security processors. The future is unlikely to belong to one universal processor. Instead, computing is becoming heterogeneous. A modern system may combine CPU cores, GPU units, neural processing units, video encoders, image processors, security engines, storage accelerators, and networking accelerators. Each processor handles the work it performs most efficiently. The CPU coordinates these components and runs the general-purpose software environment. Chapter 20. Why more cores do not automatically mean more performance. Performance cannot be measured by core count alone. Clock speed, instructions per clock, memory latency, memory bandwidth, cache efficiency, branch prediction, software optimization, thermal limits, power consumption, transfer overhead, and workload parallelism all matter. A program designed for one CPU thread does not automatically use 16 CPU cores. A program written for a CPU does not automatically use thousands of GPU units. Software must expose parallel work. Developers may need to restructure algorithms, organize memory carefully, reduce branch divergence, minimize data transfers, and divide work into GPU-friendly operations. Hardware capability is useful only when software can use it. More cores provide more potential performance. Potential performance and real performance are not the same thing. Chapter 21. A simple example, rendering a game frame. A modern video game demonstrates how CPUs and GPUs cooperate. The CPU reads input, updates players and objects, runs game rules and character behavior, processes networking, prepares the scene, decides which objects are visible, and submits rendering commands. The GPU transforms vertices, processes geometry, rasterizes triangles, samples textures, calculates lighting, applies shaders, performs ray tracing, and generates the final image. The CPU determines what is happening in the game. The GPU calculates how the game should look on the screen. Neither processor can deliver the complete experience efficiently by itself. Chapter 22. A simple example, running an AI application. Consider an AI chatbot running on a local computer. The CPU starts the application, loads configuration files, reads the user's prompt, tokenizes the text, allocates memory, loads model data, submits matrix operations, manages output generation, displays the result, and saves conversation history. The GPU performs the large matrix multiplications used by the neural network. The GPU does much of the numerical heavy lifting, but the CPU still manages the application and coordinates the complete process. The final system is a partnership. Chapter 23. The real meaning of thousands of GPU cores. When a GPU specification lists thousands of cores, it does not mean that the GPU contains thousands of full-featured processors equivalent to CPU cores. It means the GPU contains a large collection of arithmetic resources designed to work together on parallel workloads. Those resources deliver extraordinary performance when the problem can be divided into similar tasks, enough threads are available, data is arranged efficiently, branch divergence is limited, memory bandwidth is used effectively, and communication overhead is controlled. When these conditions are not met, many GPU units may remain idle. A smaller number of sophisticated CPU cores may then complete the task faster. Thousands of GPU cores represent massive parallel arithmetic potential, not thousands of independent general-purpose processors. Chapter 24. Conclusion. The CPU and GPU are both processors, but they are built around different priorities. The CPU is optimized for flexibility, complex control flow, low latency, and general-purpose computing. The GPU is optimized for massive parallelism, high arithmetic throughput, and high-bandwidth data processing. A GPU can contain thousands of units because each unit is smaller and shares more control hardware. A CPU contains fewer cores because each core independently handles complex and unpredictable instruction streams. That is why thousands of GPU cores do not replace the CPU. The CPU runs the system, manages decisions, handles irregular work, and coordinates applications. The GPU accelerates large groups of similar calculations. Modern computing is not a competition. It is a collaboration. The CPU provides control. The GPU provides parallel power. Together, they make the computer far more capable than either processor could be alone. You have been watching Gate and Kernel. Here, we explain computer hardware, processor architecture, Linux, and the operating system kernel in clear, practical language. If this video helped you understand the difference between the CPU and the GPU, please like the video and subscribe to Gate and Kernel. Thank you for watching, and I will see you in the next video.